All right. So, in this part of the for those of us that were not present in this in the class, so I'll drop a video. I'll drop this video for you so you can go through the video and all. So we did application of differentiation. So and the subtopic that we treated were the gradient, rate of change, stationary point, and minimum and maximum value. So these were the things that we treated. So we start from gradient and the formulas needed and some applications of the gradient, and we solve some examples. So from the basic knowledge of gradient is also known as slope. So the next slide provide details and informations on gradient. So as you can see clearly that the gradient, before you can look for the gradient, you must have, for cases like this, you must have your intercept, which is c to be equals to 0. So if you have an intercept with the equation of a straight line, equation of a straight line is y is equals to mx plus c. But in this case, that c that you have is equals to 0, and you have two different points, 2 point for x and 2 point for y. So the point for x is x1 s2, point for y is y1 y2. So and the gradient is in between. So making the gradient, which is also the same thing as the slope, the subject of the formula, you have m to be y2 minus y1 over s2 minus x1, which is change in y over change in x. So that is equals to dy dx. Now the first example said you should find the slope at point 1 comma 1, and you are given the algebraic function to be 3x squared plus 5x plus 4. So the first thing you have to do before finding the slope is you have to take the derivative. That is, you have to differentiate 3x squared plus 5x plus 4. Now, from your basic knowledge on differentiation, when you differentiate 3x squared, of course, you know it is 6x. You differentiate 5x, it is 5. You differentiate a constant, which is 4. The answer is 0. And you were already given points. So when you put 1 back to the derivative, you have our final answer to be equals to 11. So that's for example 1. So moving to the next example. Now, the next example that we have is on an implicit differentiation. Implicit differentiation is a derivative that comprises x variable and y variable all together. So in this case now, they want us to find the slope at 1 comma 1. One amazing thing you need to know about implicit difference derivative, especially the ones that are algebraic in nature, is that whenever you are differentiating any function that has y, you must always include the y dx. The y dx must always be present there. So it is unlike when you are differentiating the ones that are having variables of x. So as long as it is having y, you must always include dy dx. So that is why when we differentiated 3y squared, our answer was 6y multiplied by dy dx. If you differentiate sine y, which is trigonometric, your answer is going to be cos y, but you must include dy dx. Now, but our aim is to find dy dx at a certain point. So when we differentiated and make dy dx the subject of the formula, we have our answer to be minus 6x squared over 6y. And don't forget that x is 1 and y is also 1. So inserting the values for x and y respectively, we have the derivative at the given point to be equals to minus 1. So that is example 2. So the next example is going to be tangent of a curve. You are asked to find the tangent of a curve. So the tangent of a curve is also similar to finding the slope or the gradient of a function. So let's see that example. So we have equation of tangent to a curve, and the first question, equation of a tangent to a curve. There is, if you recall from your circle theorem from your basic secondary school days, a tangent is a line that is passing through the top surface of a circle. So you have equation of a tangent of a circle. You are asked to find the equation of the tangent to a curve. So it simply means that the curve given is x squared plus y squared is equals to 5. So this is a curve at point 1 comma minus 2. Now the formula we'll be using in this case is slightly different from the first formula that we use in finding our gradient. It's almost the same thing, but in this case, instead of us using y2 minus y1 equals to mx2 minus x1, we'll be using y minus y1 equals mx minus x1, where x1 is 1 and y1 is minus 2. X1 is 1, y1 is minus 2. So the next thing is us finding the derivative, and this is an implicit derivative. So by differentiating it implicitly, just like what we did earlier, differentiate x squared, that's 2x, differentiate 2y, you have to include the dy dx and you equate it to what? 0. Now when you take the derivative of this and you make dy dx the subject of the formula, you have minus x over y, which is equals to what? 1 over 2. So the 1 over 2 that we've gotten is our m. Now how did we get 1 over 2? Don't forget that our x is 1 and our y is minus 2, and there's a negative sign there before, so the negative sign cancels out, so we are left with 1 over 2. So therefore the equation of the tangent to the curve, that shortcut, that ETTDC, simply means equation of a tangent to the curve, will therefore be the formula that we stated above, which is y minus y1. So our y1 is minus 2, our x1 is 1. So when you insert everything, we have y plus 2 is equals to 1 over 2 x minus 1, and when we do the necessary arrangement, we have the equation of the tangent to be 2y minus x plus 5 equals to 0. So when you are seeing questions, when you see questions on equation of tangent, so these are all of the process that you should follow before finding the equation of a tangent of a curve. Meanwhile, don't expect questions on algebraic functions alone. You can see questions on trigonometric functions, where they will ask you to find the equation of the tangent to the curve. You can see questions on exponential functions. You can see questions on logarithmic functions as well, such that they will ask you to find the equation of the tangent to the curve. So practice all through. Don't just limit yourself to only algebraic functions alone. So the next thing we have is rate of change. When we say rate of change simply means that you are changing some certain parameters with respect to another parameter. So but in this case, we have a lot of things that we can do under rate of change, but the ones that we lay our focus on are the physics terms that we know, the common physics terms that we know, like displacement, which is also distance, speed, velocity, acceleration, and all. So we check out their, so for example, we check out their necessary parameters. So the first one, if you have a displacement, or provided you have a distance and you're asked to find the rate of change, what they're asking you to do is take the derivative with respect to time t. So when you differentiate or take the derivative of displacement or distance, you have your speed or velocity. So likewise, if you differentiate velocity with respect to time, you have acceleration. So what does this imply? It simply implies that when you are asked to find your acceleration and you are given a displacement, it simply means that take the derivative of the displacement twice. So taking the derivative of the displacement twice will give you your acceleration, provided displacement is not given, provided velocity is not given. But if the velocity is given and you're asked to find the acceleration, just differentiate the velocity once, then you have your acceleration. Likewise, you can also have the third derivative. The third derivative is jerk, right? So if you differentiate acceleration, you have jerk. You differentiate Jake, you have Jones. That's the fourth derivative. So you keep on going like that till you snap and pop the fifth derivative of displacement. So it keeps on going like that. So the parameters that will be checking under rate of change, you can take the derivative of anything. You can take the derivative of rice with respect to beans, take the derivative of spoon with respect to anything, as long as the necessary parameters are given. So you are not limited to finding dy dx only, right? You are not limited to finding only dy dx only. So by the time you are doing rate of change, that's when you'll be introduced to other types of derivatives that we have. So these are the basic three ones, the basic three that you'll be dealing with. So the next slide, will solve an example under rates of change. So as you can see clearly, we have an example. We have a distance, a body moving, a particle moving with having a displacement of 60 squared, 60 cube plus 3t squared plus 60, all in meter. So the unit for displacement is meter. Is either you are saying displacement or distance, they are the same thing. It's only that one is a scalar and the other one is a vector. So you are asked to find the speed, the velocity and acceleration at t is equals to 1. So what we do is we take the first derivative. Now the first derivative, you can see displacement to be represented with r. You can also see displacement to be represented with x. You can also see displacement to be represented with capital letter X. So these are the three ways you can see displacement. So when you see r, or the unit can easily tells you that okay, this is displacement. So when you take the derivative, you have 18t squared plus 6t, and at t is equals to 1, at the time of 1 second, you have the velocity to be 24 meter per second. So that's the derivative, which is the velocity. Now you take the second derivative again to find the acceleration. So to find the acceleration, you differentiate the velocity. So on differentiating the velocity, you differentiate 18t squared, you have 36t plus when you differentiate 6t, you are going to have 6. So you can easily change that, change the so what you were meant to have should be 36t plus 6. So you'll be having 36t plus 6. So it's going to be 36 times 1, which is 36 plus 6. 36 plus 6 should give you 42. So our final answer for the final answer is going to be 42 meter per second squared, not 36 meter per second squared. So kindly change that error. That's a derivative error. So the second derivative should be 36t